Now friend, we again come back to last part of this video lecture. So now here I'm talking about these three atom, or you can talk about, I can talk about this atom, this one and this one. So if these three atom are placed close to each other, then there is some void space. Okay, so it will look like it's look like a structure like triangular shape. Okay, if it is come close, then if this one is come close, then there might be a one shape. That shape is look like a triangle. Okay, so in solid, if you synthesis your material in different way, suppose in hexagonal structure, in monoclinic structure, in cubic structure, then tetragonal structure, they produce a different close pack on layer over the another layer. There is creating a different kinds of void structure or void that is called as sometime octahedral void, or sometime it is called as tetrahedral void. Let us see with an example of MgFe2O4. Here this corner atom indicating in the blue color, that is the Fe atom, iron atom. Okay, this is the tetrahedral position, and this is also tetrahedral position. This is also, I will let you know what is tetrahedral and octahedral position and why it is called a tetrahedral, why it is called as octahedral. Okay, so if I observe carefully, so this is look like very complicated. Okay, so here it is green and black. They are actually combination of magnesium and combination of iron. Okay, and simply this is blue color indicating the only iron is present here, and this is the anions which are surrounded with the atom of cations, because here it is magnesium, it is a cation, and Fe it is a also it is a cations, and oxygen it is a anion here. What if I am remove the oxygen from the structure? It is look like just little bit of simple. Now if I put the oxygen again, it is look like a complicated. So let us simplify one by one, and I will discuss the position of atom and what is the importance of position of atom, because earlier we know the direction and Miller indices and HKL planes, how to calculate manually, that I show earlier. So let us find the values of or position of atoms that produce a void. Okay, so now I'm going to remove the all oxygens, and I remove the bond also from this structure. So this structure now it is look like this in the cubic. So inside this cube there is a combination of magnesium and iron, because I'm already told you this black and green combination show here the combination of iron and combination of magnesium. This is two atoms is there, so they are combined each other, so at the same place, and produce a octahedral geometry. So this octahedral geometry that is inside the cube, and the tetrahedral geometry that is at the corner of the cube. Okay, so you find the each and every corner having the single atom, and this top view of the cube, if you observe carefully, so this blue atoms, this blue one at the corner, and one blue which is present at the top face. Okay, so this is called as face center cubic. And what about this atom which is present inside? This produce a diamond like structure. Okay, how it is produce a diamond like structure, and because of that what is the strength of material change, and what kind of physical property also showing this material, that I will discuss in the later part of this video. Okay, friends, if we are observe this structure carefully by little bit of zooming in, so this corner atom, if I am talking about this corner atom, suppose about this corner atom, so if you look about this corner atom, so there is a 1, 2 and 3 atom at the bottom and 1 atom at the top. So these 3 atoms at the bottom, they mix with the top atom, they makes a geometry. That geometry is called as tetrahedral geometry. okay, or this site is called as tetrahedral site. Like this, if you observe the center one, okay, this black and green, they produce a octahedral geometry. Let us see polyhedral type of nature. So it is look actually like this inside the crystal. So it is look very attractive inside the crystal. So this is the tetrahedral geometry, and this geometry is a octahedral geometry. If you observe carefully, so this tetrahedral sites which are present only at the corner atoms, okay, so this is corner, this one and this one, and at the face also, okay. So it is look like a little bit of difficult to understand. So let me simplify the structure with a different manner. So let me remove the bonds and also the octahedral atoms or octahedral sites from this structure. So I will remove one by one. So it will remove all the octahedral structure. Now friend, in these structures there is only present of some corner atoms 1 2 3 4 5 6 7 8 and face centered. This is one for 6 faces having the 6 face center, okay, 1 2 3 4 5 and 6. Beside this 6 atom present at the 6 face and the 8 atoms present at the 8 corners, there is also 4 atoms which is present inside the cube. Let us see how it is inside the cube, okay. So these 4 atoms, first, second, third and fourth, this 4 atom is inside the diagonals of the 4 corners, okay. So this atom from the diagonals, from starting from this corner to the diagonal of this corner, means from this diagonal to this diagonal, this atom is here. From this diagonal to this diagonal, this atom is here. Now from this diagonal to this diagonal, this atom is here, okay. I know it is look like somewhat difficulty. Let me show in a different manner. So let us try to draw a diagonal. Okay, so mark first the atom those are present at the corner and at the face. This is first atom, this is second, and this is the face center of the first top, and this is the again corner. This one is also corner, this one is also corner, this one is also corner. So here 1 2 3 4 5 6 7 8, okay, this 8 corner is equal to 1 atom, and 1 2 3 4 5 6, this is 1 2 3 4 5, and this 6 is nothing but a 6 by 2 because this is at the face, so it is sharing half of the portion to this unit cell and half of the portion to the another unit cell. So 8 corner, that is 1 by 8 multiplied by 8, then 6, then divided by 2, nothing but a 3 plus 1 4. That means this 4 atom which is partially share, and 1 2 3 4, that 4 atom it is totally sharing with this unit cell. So that means this is a 8 tetrahedral geometry which is present in this structure. So that is why this sites is called as 8 tetrahedral sites. You understand what is the 8 geometry, right? So this is 1 by 8 multiplied by 8 corner atom, then 1 by 2 means half portion sharing by this face center and 6 faces, and this 4 1 2 3 4, that 4 is sharing with total part, means entire part of this to the unit cell. So that is why it is a 8. So this is called as 8A site, that is indicating tetrahedral site. So now draw a diagonal. The diagonally, that means if I draw a diagonal from this from this diagonal to this diagonal, so what happened? I can draw from this diagonal to this diagonal. So there is a one atom which is present at the diagonal. If you divide this diagonal, that means from here to here it is a 1 by 2. So from here to here it is a 1 by 4th. So that means it is 1 by 4, 1 by 2, 1 by 3, then 1 complete. Okay. Now let me draw one more diagonal from this diagonal to this diagonal. So again from the position of this origin here to this point, this is again 1 by 4th portion inside the diagonal or inside the cube, and from the center to the diagonal at the position of 1 by 4th, this atom is present here. Now let me draw one more diagonal from this to this one. So it will cut this one like this. Okay. So again this atom which is present here, it is look like 1 by 4th part which is sharing here, or at the position of 1 by 4th part. Now draw the last one from this diagonal to this diagonal. So it is again starting from the origin, it is 1 by 4th. At the position of 1 by 4th, this atom is shared here now. So that is why they produce octahedral type of geometry. And now discuss the tetrahedral geometry, how it is all happening or produced inside the crystal structures, which is called as 16C or 16D. Friends, let me tell one more thing about tetrahedral site. This 8A, which is nothing but a tetrahedral inverse site, and somehow people also find the 8B, which is called as tetrahedral normal site. Okay, so 8A, which is the inverse, and 8B which is a normal. Normal means this is present at the center, this atom which is present at the center, this atom which is also present at the center, that means it is a normal. From this normal, if it is go to inside or outside, then it will be inverse. Okay, as like a mirror image. You can see from the distance of mirror, so you will find the same distance from you and mirror, so it will look same. Okay, from the center, if it is go inside, then also it is inverse. From the center, if it is go outside, then also it is inverse. Only in case when it is present at the center, then it is called as normal. Okay. Now friends, if you change this tetrahedral atoms or in geometry, or remove this tetrahedral from this unit cell, you will find this one is like this. So this is actually the atoms which create a octahedral geometry. Now I remove the tetrahedral. This blue are the tetrahedral. Now I remove the blue, and I put the here magnesium and Fe, which is mixed and which produce a octahedral geometry. That octahedral may be 16C or 16D. Let's find how is it happen. Okay, so let me again show by using the diagonal. This structure actually MgFe2O4. So if I put the oxygen, that is nothing but an anion, this structure is look like this, complete structure. If I am doing the structures like this, then it will look like this. So one by one I will remove. Earlier I was remove the octahedral geometry. Now I will remove all the oxygen atoms and all the tetrahedral geometry, and only I will put the octahedral. Later on I will show the connectivity between the octahedral and tetrahedral, and what is the importance of this octahedral and tetrahedral geometry inside your structure. So let me first remove this polyhedral shape. I will remove this one. then I'll remove the oxygen atom, then I will remove the bonds, then after I will remove this tetrahedral geometry, this one. Now it is completely look like this. So it is all the atoms are present inside the cube. So let me count this cube, how many inside the cube, how many atoms are present. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So 16 atoms, which is exactly 16 atoms which is present inside the cube. See, no atoms are present outside the cube. So that means this kind of structures named as 16C or 16D, which is the basic name of octahedral geometry. If it is inside from this origin, then it is inverse. If it is outside from the origin, then also it is inverse. But if it is in the corners, then it is a normal. So it is inside, that means from this corner atom to here it is also inside, this corner to here it is inside. Okay, no atom present at the corners. Okay, corner means it is a origin, so no atom present at this original position, such as origin. So that is why it is called as inverse. So inverse indicating 16D. So 16D means it is a octahedral geometry. This is the structure of MgFe2O4 only with octahedral geometry. So if you observe this structure carefully, we'll find from this face to this face there is a one slope, look like this. See, 1 2 3 4, these 4 atoms are connected from this face to this face. Okay, so that means it is a diagonally, not it is a diagonally, but there is a slope which is connected from this face to this face. Like this, how many faces is there? So there is a 6 faces. So 6 faces which are connected to each other by diagonals. Okay, so this is one face. And if you observe carefully, okay, now earlier I am talking about this 4 atom, 1 2 3 4. So this one is diagonally from this face to this face, not actually diagonally, this is slope. Okay, likewise this face, this corner face is connected to this corner. Okay, likewise this 4 atom, 1 2 3 4, it is connected from this corner to this corner. Let me move this one and show it like this. Okay, just concentrate on this 4 atom, this 4 atom. Okay, so this one from this corners to this corner, both are connected by using these 4 atoms. Okay, and from this corner, center from this corner to the center for that corner, which are again connected with this 4 atom. Likewise all the corner to corner or face to face, they are connected in this manner. Let me connect one by one. First, these 4 are connected from this corner to this corner, means this is the first face, the front face, and this is the back face. So they are connected like this. Okay, and from this corner of the first face and this corner of the second face, they are also connected like this, isn't it? Okay, now from this corner, means this line to this line, they are connected like this. Okay, and from and from this face to this face they are connected like this. Now I may draw this figure, this line from this surface to this surface, and from this top surface corner to bottom surface corner. Okay, and from this top surface beside of this corner to this bottom, and from here to this bottom. So it will make a octahedral geometry. Okay, so this is actually the diamond structure, means cubic diamond structure created inside the cubic or inside the cell. So this position of atom is, suppose this is divided into 1 unit area or 1 unit length. This is 1/4, this is 1/3, this is 1/2, and this is 1. So like this they are distributed from one surface corner to the another surface corner. So if you count this surface corner to surface corner, so this is red 2, then blue 2, 4, and this black 2, so 6. So 6 faces. From these 6 faces it will come from the 6th plane. So using this parameter or using this plane, they produce a Miller indices. Okay, and they find the atomic density on this plane, and regarding that atomic density, the density or the planes which, the number of planes which is present more in a solid material, that will shows the maximum intensity in the X-ray diffraction pattern. So if I combined this tetrahedral site and the octahedral site, this is 16C site, which is also called as octahedral site, then it will look like this. So inside this there is a 8 and 16, so 24 atoms are present. 24 atoms are present inside the cube, and this 8 atoms are present at the corner. So therefore this is the combination of the complete part of MgFe2O4, including the anions and cations. Now friend, let me show the connectivity between this atom and this atom. So this is the tetrahedral geometry and this is the octahedral geometry. So let me show the connectivity and the bond length and the what are the bond angle between them. Okay, now if I remove all the tetrahedrals and octahedrals, just put 1, 2 and 3 here, then it will looks very clearly visible like this one. Okay, so this is actually one face of the cubic. This is corner. Now let me show how this tetrahedral geometry is connected to the octahedral geometry. Okay, now again I am removing some parameter, some atoms from here to here, so it will look like somewhat like this. So if you observe carefully, then here you might observe the connectivity between the octahedral and tetrahedral. So I can show you more clearly. See, it is the connection between octa to octa, tetra to tetra, and octa to hedra. Okay, so in this manner they are connected like this. If I remove this square, we will find it is again more clearly visible. So this is actually they are connected. See the geometry, how they are connecting, and how the octahedral and tetrahedral they are connected. See this bond, this green and red and this blue and red bond, they are connected and they are making an angle. Okay, So this is called the bond angle. So this is all these parameters depends on the material your synthesis and the technique your approach, whatever technique, chemical method or physical method, wet chemical method, whatever method you have used, and the stoichiometric ratio and the ionic radii. So this is depends on that parameter. So friend, this image or this diagram you can draw whatever the X-ray diffractional pattern you get from the machine by solving some ritual refinement method. You can draw or you can analyze each and every part of your material. So I hope now you understand the octahedral and tetrahedral geometry and the connectivity and the bond length and bond angle between the solid to solid, and the atomic density inside the cube or whatever your structure. Okay, it may be hexagonal or it may be tetragonal, whatever the structure. It is depending on the structure and depending on the atomic crystallographic direction, Miller indices. So out of this you can solve your material such that you can understand very clearly of your material. See, if I use the polyhedral, then it will look like this. See, this is tetragonal geometry, this is the octahedral geometry. They are connected and they also produce a void space between this. So in this void space, that it maybe captures some orientations of atoms or rotations, anything. So there is a versatile applications of this void space between the octahedral and tetrahedral geometry. Because of this, your material is getting some importance. Sometime it is happening in the due to the defects in a crystal. So I will discuss in the next lecture how to manually calculate using the software, how to calculate from the XRD data lattice parameter and X-ray density, bulk density, and so many parameters which is come out from the X-ray. X-ray is a versatile or very vast area of research when you go through your structure of your material. Friends, while I am talking about structure, means it is the key research part of your research, whatever may your topic, that everything is depends on the structure of your material. So I request you please focus on the structure. So please continue with my lecture. I will make another video on real data which is coming from the X-ray machine and how this data is converted like this type of structure. Thank you very much.